Yeah, hi. Good evening, everyone. Welcome to the session. So this week we have to plan to discuss our week 8 and week 9 that assignment questions. So that we will discuss today. Sayan and Pulkit, can you start?
Yeah, sure, sure. Okay, so this is week 8 programming assignment question 1. And the problem statement is during the Koryo dynasty, a dedicated group of royal messengers known as the peasant riders carried vital messages across the kingdom. They relied on a network of hidden routes and secret outposts to move quickly and cautiously between provinces. Now, a crisis takes shape over the land. An invasion from the northern steppes threatens to cut off the communication between the capital fortress and the sacred mountain, where the last resistance army is preparing for the battle. So our task is to determine the maximum number of days the messages can be delivered to the resistance before all routes are compromised. Each route between outposts is a one-way path, and it can only be used once before it falls off under the enemy control, making it permanently inaccessible. So, as a leader of peasant riders, you must find the maximum number of days messages can be delivered before every route from the capital fortress to Sacred Mountain is lost. The input format that is given to us is the first line contains the T, which is the number of test cases, and for each test case, we have a line with two space separated integers representing P and W, where P is our nodes or the number of outposts and which are numbered from 1 to P, and W represents the number of one-way routes between them, or basically kind of edges. The next W lines contain two space-separated integers U and V, representing the one-way route from outpost U to outpost V. So if we look at a sample input, for example, we have one test case here. The value of P is 4 and the W is 5. That means there are 4 nodes here which are numbered from 1 to 4. So like 1, 2, 3, and 4. So W is there are 5 edges. And these are the edges that are defined. So 1 to 2 here means there is an edge from 1 to 2, 1 to 3, 2 to 3, 2 to 4, and 3 to 4. So 1 to 2 is one edge, 1 to 3, 2 to 3, 2 to 4, and 3 to 4. Now one more thing that was given to us in the question, that each route between outposts is a one-way path and can be used only once before it fails off under the enemy control. So that means the flow of the network that is flowing for each of these is of just power 1. So like in this diagram here, each of the flow will be of just 1 unit here. So our task is to find the maximum flow that can be flown here. So one way to do this is if we send a message from 1 to 2 and then 2 to 4, the routes between 1, 2 and 2, 4 will become compromised. So this is we can do on one day. On another day, we can send the flow from 1 to 3 and 3 to 4. So after 2 days, there will be no more routes. So the area will be completely blocked. However, if we send it like from 1 to 2 and 2 to 3 and 3 to 4, this is also one possible route. But in this way, we can only send messages to one day, because from 1 to 3 we can go, but from later part it is blocked. So that was a problem statement, that we have given a source node P from where we will start, and we have to reach an end goal. And this problem is basically to find the maximum flow, and we will solve it using the Edmonds-Karp algorithm, which is a BFS version of four-Colson algorithm. So for that, first we will define a function for the BFS, in which we will take the source and sink, which is like starting node and the ending node. So we'll create a visited set and a queue in which we'll start with the source node and we will add the source node to the queue. And while our queue is not empty, we will pop the element from there and we will explore the neighbor of the U. And if it is not in the visited, also the capacity of U to V is greater than 0. That means we can flow the network from there or we can pass that route. Only in these two cases, when these are satisfied, we will create this parent of V to U. So this is to keep track of the path. So in this way, we are keeping track of the path that first we go from U to V like that. So U is the parent of V here. And then we are adding the visited to the set. And if V is our final sync node, then we will return true. Else we will append the V to the queue. And in the end, if the queue is empty and we have not found the sync node, then we will return false. That means there is no path from the source to sync. So now we are defining our admin scarf. So first we are initializing a parent array. That was the path that we will use here. So here we are setting it to -1 of LAN of capacity. That is basically the here. It is of matrix of order p into 1 of p into 1. So we are creating a node matrix of all. So this we are passing it here. So the LAN of capacity would be same as the number of nodes here. And initially we are setting the max flow to be 0. Then while there is a path from source to the sink, we are creating this path flow variable, which we are setting to a infinity variable and s variable with the sink. That is our final end goal. And now we will do the backtracking. While until we don't reach the source node, that is the starting point, we'll take the minimum of the path flow, that is this infinity variable, or the parent of s, that how we reach the sink. So if u to v, so we are starting from v, so the parent of v would be u. We are taking the capacity of that. So capacity was the edge that was going there. So the minimum of the path flow, that was this infinity variable, and the edge flowing from there. We'll take the minimum of that and set it to path flow variable. And we will update our s with the parent of the s. So if initially it was v, now it will become u. So in this way, we are backtracking the path. Now we are again initializing here with v to be sync. And until v is not the source path, here we will update the capacities. So that is the flow that is flowing from there. We are setting the u to be the parent of the v. And then from u to v, we will decrease the path flow. And from v to u, we will increase the path flow for the reverse backtracking. In case we further find a more optimal way of reaching that, we can backtrack it. And then again, we will set the v to be parent of v. So in this way, we will keep updating. And in the end, we will update the max flow to the path flow value and return the max flow. The later part is almost similar to any of the question, that we are taking the number of test cases as the input. And then for the number of test case, we'll run a for loop. And first we will take the two integers, p and w, where p was the number of nodes, which are numbered from 1 to p, and w was the edges. So we are creating a capacity matrix. So it will be like kind of, for the example that we had here, 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4. Initially, it will be all like 0, 0, 0, 0. And then we are running the for loop for the number of weights. And we are taking those two integers here, these two one by one. And if they are not equal, that means there's no an edge from a node to itself, Then we are updating the adjacency matrix here, adjacency list, sorry, with the pi from to pj and from pj to pi, and the capacity value also we are increasing by 1. So here, as there is a node from 1 to 2, the value from 1 to 2 would become 1. And similarly, like this, we are filling the capacity matrix, and the adjacency list would be just if there is a path from 1 to, we can go to 2 then 3, and from 2 to 3 and 4, and from 3 to 4. So like that, we will update our adjacency matrix. So it will be like both way, from pi to pj and pj to pi also. And then we are running this admin cards function here that we define, and passing the source function, source node to be 1, the sink node to be p, the capacity matrix, and the adjacency list. And it will return the maximum days, which is basically the max flow value, and we are printing that. The code is pretty much similar for other languages. It's just that we are defining the infinity here with this hexadecimal value, and rest part is same for this one also. And for Java, we are using the integer.max value for the infinity. So, any doubt, anyone? Okay, then you can start.
Yeah, so let us see the week 9 uh, question and the solution for that. One second, let me share the window. Yeah. Yeah. So in this question of week 9, so we just have one question in this week. So here, what you're given is that you are basically a microbiologist and you're maintaining an ecosystem in your lab, and it has multiple different bacteria. So they have basically created a food web in their ecosystem as they usually do, and they feed on each other and also help each other. However, what I've found is that some of your bacteria are dying. So in the real world, you would just let it play over, and weak ones they die, and the strong ones they survive. However, as you are actually maintaining an ecosystem, you want to actually let all of the bacteria live, or you want to save as much as possible. So you are seeing that there's a like discrepancy in the food. So some are not able to find food, whereas some have excess food. Right? So what you have to do is you have to basically do a redistribution of the food. So you have to find the bacteria that are multiplying at the fastest rate and the one that are dying at the fastest rate, and redistribute the food from the one that have excess to the one that have less. Right. So to do this, you basically, there are multiple ways, but you decide to create n pathways in the ecosystem. So what the pathway will do is it will just connect two clusters of bacteria, and simply by the how osmosis works, the place where there's a high concentration of food, it will automatically move towards the place with a low concentration if they're connected. So the path will be unidirectional. It will always move from the higher to the lower, and you decide to create n such pathways. So you might require more than n, or you might require less than n, but you decide to create n pathways to do this. And each pathway will take resources from a group and give it to the other group. So they are directed, and no two pathways will go to the same cluster of bacteria. So this is basically our first hint. So what this means is that we are basically working with a matching problem in a bipartite graph. That's what basically means is we basically have two distinct groups of nodes in the graph. So although all of them are nodes in the graph, all of them are bacteria clusters. There are some which are in excess, and there are some which are in deficit. So we have two types of nodes. So we have a bipartite graph, and because no two pathways will go to the same cluster, that means it's a matching problem. So here we assume that a path has enough bandwidth to help the cluster that it is feeding. So we don't assume that there's any bottleneck or choking point in the pathway itself. However, since the paths are long, the food transmission is not instant, so it'll take some time. So it'll take time to reach the cluster. And in each pathway is traveling at its max possible speed. So there's nothing you can do to speed it up. So the speed directly depends on like how far it is and the other things in the clusters. So if let's say if we have the n pathways, then for the n pathways, we have the speed for each of those pathways. So we denote that as SI, and that is in units per minute. So because this is in a microscopic world, so not the classical physics don't really work in this world. So here the time is not really distance by speed, but rather it's distance by speed squared. So this is because there are some forces like weak nuclear forces and strong nuclear forces, which are actually dominant when seen in this microscopic scale. So they become negligible in larger scale, but in this scale, the weak nuclear forces are dominant. So the time taken is the normal Euclidean distance divided by the speed squared. So you declare your mission a success. So in the end, you want to make as many clusters survive as possible. So you don't need to make all of them survive for it to be a success. So you just need to be able to save at least k clusters, right? So that you can save k clusters, you have to find the minimum time required to complete this mission. So obviously, if there are two pathways, one which takes a lot of time and one which takes less time, and you just want to save one cluster, you will obviously choose the second pathway so that you can just do it in the less time. That's what we have to find here. So this is again a matching problem where you have to minimize. So the minimization of what we want to do is the time required to complete. And the time we can directly get by this formula. So we take the distance and we divide by the speed. So the input format is pretty similar to the previous week. So we have T, which is the number of test cases. And then we have N, M, and K. So N is the number of pathways that you have decided to create. M is the number of dying bacteria clusters. And K is the minimum number of clusters required to recover to call it a success. So the next N line contains two space separated integers, xi and yi, where I belongs to 1 to n, and denoting the position of the start of the pathway for the ith pathway. The next timelines contains two space separated integers, pj and qj. So this denotes the position of the jth bacteria, the jth dying bacteria cluster in your ecosystem. Right. So basically, start of a pathway is nothing but a position of the surplus clusters. So the clusters that have surplus. So your pathways obviously start from the surplus ones, and they go to any of the dying ones. So you have to decide which dying one to go to. Right. So each pathway starts from a surplus cluster. So that is assumed. But then we have to choose which pathway goes where. Right. So the next end line contains space separated integers si to si, where I belongs to 1 to n. So these are the speed of the pathways. Right. So these are a few of the constraints of these. So we have at max 10 test cases. The number of pathways is at max 200, and the M, which is the number of dying bacteria clusters, that is also at max 200. And K is obviously less than N. Right. So you cannot have more than N number of maximum, like minimum clusters you want to save. And then the values of xi, yi, pj, and qj. So these are the coordinate system values. So that can be at max 10 to the 6 or 1 million. And the speed also, it belongs from 1 to 50. And then the output is simply 1 or 0. So the output is the minimum time required to reach the cluster. But if it is not possible, then you have to print -1. Right? So this is a simple example here. So you have one test case where we have 3, 2, and 1. So what are these values? 3, 2, and 1. So this is N, M, and K. So we have 3 pathways, 2 dying clusters, and at minimum, we just want to save one of these dying clusters. And then these, after that, we have N lines, so 3 lines, that is the pathways, right? So 1, 1, 2, 2, and 3, 3 at the start of the pathways. Then we have M lines, which is the dying clusters. So 34, 59, and 14, 20 are the dying clusters. And finally, you have the speed of the pathways. Right? So let us try to sketch this out. Right? So you have 3 surplus bacteria at 1, 1, 1, 1, 2, 2, and 3, 3. So I'm assuming that the coordinate system is like this. And similarly, we have the 2 dying clusters at 34, 59. So that would be somewhere way off. So 34 around here, 34, 59, and there is 14, 20. So it will be somewhere closer, 14, 20. Right, and then we have the speed. So this one has a speed of 1, this one has a speed of 2, this one has a speed of 3. And then we have to find out the minimum time required. So in this, obviously, we just want to save one of the 2 clusters. So this is dying cluster 1 and this is dying cluster 2. So the closest one that we can save is obviously D1. Right, so to complete this mission, one pathway should reach its destination. So we see that the pathway at 3, 3, so this is the closest, gets this goal done in the minimum time. So this distance would be minimum. So here this is 14, 20. So this one is 3, 3. The 3, 3, this is 2, 2, and this is 1, 1. So if you see the distance and then you do the by speed, right? So this also has the highest speed as well. So this has the highest speed and the lowest distance. Obviously, this is going to be the minimum time. So if you simply do the t equals the Euclidean distance, so 14 minus 3 whole squared plus 20 minus 3 whole squared whole by not 3 but 3 squared. So then you get, so this is 11 squared plus this is 17 square. So if you divide this by 3 square, which is 9, right? So what will be the value? So 11 square is simply 121 and 17 square is 289. So this is 121 plus 289 by 9. So 121 plus 289 is 410 and 410 by 9 is 45. Right? So this is 45. And if you then multiply that with 60 to get the seconds, you get the answer of 2760. Right? So this is 45 point something. So if you do that times 60, you get 2760 seconds. Right? So that is basically how you solve this question. So you have to find the matching or the minimal matching where so this is for k equals 1, but then if as many, whatever is the k, you have to find that many matchings where you minimize the distance, right? So, or the time. So for one case, you just minimize the time, and for multiple paths, you just minimize the sum of the time. Right? So let us see how to solve this. Okay, so this obviously uses the Kunz algorithm to find the minimum matching. So we won't be going through the details of the algorithm itself. So here we'll define a graph. So the G is the graph that we're defining, and the LR and the vis variable. So then we have a helper function, which is the DFS function. So this simply performs the DFS, the DFS search that we have studied in previous weeks, which is used by the Kunz algorithm. And this is again the default Kunz algorithm, right? So we are just finding the minimal matching in this. So finally, in our driver code, we take the T, which is the number of test cases. We iterate that many times. For each test case, we take the N, M, and K. And then we take also the X1, Y1, X2, Y2. So these are the pathways and the pathway coordinates and the dying bacteria coordinates and the speed. Right? So all of these are initialized to 0. And then we just load them using the inputs that are given. So first we load the X1, Y1, which is the pathway coordinates, start of the pathway coordinates, and then the X2, Y2, which are the dying clusters coordinates. Finally, S, which is the list of all the speeds. So obviously, if you want to save k clusters, but there are only m clusters, which is less than k, then it is not possible. So we print -1 and we move on to the next test case. So otherwise, we basically have to find the best matching. So we basically do a binary search kind of a logic. So we take L equals 0 and H equals the lim. And as long as L is lesser than M, right? So you can see we are doing a binary search. So we are taking a mid equals L plus H whole by 2. And if you're using any other programming language, so there, make sure that this does not overflow. So in Python, it is fine. However, if you're using C, C++, or Java, you might want to do L plus H minus L whole by 2 instead of L plus H whole by 2 to avoid overflow errors. Right. So, and then once we find the mid, then for that mid, like we iterate over all the pathways and all the dying clusters, and we get the speed, right? So speed is not like the speed squared. So we take the speed and we multiply and we get the distance. So this is the Euclidean distance, x minus x squared and y minus y squared. And we just get the time required. So this is just p by s whole sealed. So if that answer is less than the mid, so if that is lower than our middle approximation, then we simply add it to our graph, right? So from I to j, right? So it's obviously a directed bipartite graph. So we're going from the surplus clusters to the deficit clusters, right? And we do this for all of the, so we do this for each binary search iteration. We do it for all the combinations of source and sink. And so then again, for each binary search iteration, we find the answer, which is simply done by using the Kunz algorithms. And if that is greater than k, right? So it's greater than equal to k, then we are getting closer to the solution. Right? So then we do an equals mid and h equals mid minus 1. So we basically split our search space by half. And otherwise, we still split our search space, but we move to the above, right? So we move the lower bound to mid plus 1. And then finally, you should note that all the amounts are given in minutes, but we have to print it in seconds. So in the end, we have to print the answer multiplied by 60. Right? So that is how to solve this question. We also have similar solutions in C++ and C and Java. So the logic remains exactly the same. So the DFS kun and the driver code, they are all doing the same thing, just the syntax changes. Also, you have to ensure that if you need somewhere to store a big number, that you're doing that in a long. Right. So that is the week 9 question for the minimum cut. So if there are no other doubts, then we'll end today here.
Okay, thanks. And any query, anyone? Okay, so we received a very common query regarding the how the marks will be evaluated for this assignment. So because that contains both type of assignments, programming and quiz. So for quiz, actually, you know that 25% marks are taken from the assignment and the remaining 75 taken from the exam. So for 25% marks, 12.5 marks will be taken for 8 out of 12 quiz. Okay, so you have total 12 quiz in your 12 weeks. Now, for the same type of ratio, we will take in from the programming elements. Like suppose if you have 24 programming graded questions in 12 weeks, so same ratio like so 66%. So how much it will be there? 16 question. Okay. So best 16 question score will be taken for the remaining 12 point. So same ratio we will be taken from that programming person, and that will be considered for the like 25 mark, 5 marks for this. And exam will be based on this like MCQ, multiple select, and numerical input type of question based, and not programming writing code. Okay. So these are very common query on the like forum also, and that form also. So I hope this is clear. If you have any query, you can post on the like forum, okay, of this course. Thank you. If no query, then we can close the session. Thanks, everyone.
Thank you all. Bye bye.
Thank you.